Good morning, everybody, and welcome to the third and final installment on recommendation engines. This one is the secret behind recommendation engines. My name is Michael Esposito, and I'll be your presenter for this particular webinar. I'm a director and data scientist at Analytics. I've been working with SAS since 1992, including nearly 7 years at SAS Institute Australia, working in technical support and consulting. I've nearly 30 years experience with SAS. Currently, I'm an independent consultant and instructor, teaching statistical and data science courses on behalf of SAS Australia and New Zealand Education Services. In 2010, I started my company Analytics and have worked in close partnership ever since with Selerity, especially on projects which require analytical expertise. Before we start, there are some housekeeping items I'd like to cover. Today's webinar will be available to watch after the live session, and you can access it using the same link you're using now, as well as via the Selerity YouTube channel. We want your feedback. We'd love to hear from you during today's presentation, especially if your feedback is nice and positive. If you don't want to hear any sort of negativity, if you're having a bad day, you can keep that one to yourself. Use the Q&A tab at the top of the chat window to provide your feedback, please. We'll be answering questions at the end of the session, but if we don't get to your question today, we'll be sure to follow up with you afterwards. About Selerity. Selerity are committed to increasing the overall productivity of organisations that they work with around the world. They offer a wide range of services from SaaS installation to administration to on-demand support services and several other of their own technologies. Selerity helps organisations gain better insights quickly and more efficiently. They have a dedicated team and their clients benefit from reliable and cost-effective expertise, available anytime, anywhere. They understand the importance of expedience and how SaaS users simply want to turn on and use their systems knowing that they're getting the right insights as quickly as possible. What are we going to cover today? If you've not already watched it or attended the first two webinars, I strongly recommend, did you hear what I did there? Strongly recommend that you go back and view it on Celerity's YouTube channel. As this webinar is also being posted to the channel, a link to previous webinars will also be in the description for this video when it is uploaded. So what we're covering in this episode is extending the recommendation system that was first discussed in the previous episode. I'm going to cover some very minor, very simple, almost trivial data preparation, simply involving converting numeric variables from measures to categories. I'll be talking about matrix factorization. So the recommender system that we'll be developing this morning, is actually based on factorization machines. So therefore matrix factorization is the heart of the algorithm. And yes, there will be a few equations for those of you who are so inclined. We'll cover hyperparameter tuning, because there are several hyperparameters about our factorization machine that we need to specify. And we'll finish off with scoring, both by inside the factorization machine itself and also exporting the model as score code and applying it to a data source outside of the application. So let's move on to extending our recommender system by virtue of applying a statistical algorithm known as factorization machines. Methodology: we'll be building a recommendation engine based upon factorization machines. So new predicted ratings are based on user factors, item factors, and also the interaction between user factors and item factors, even though a user may not have rated a particular item. We'll be generating some scoring code to run in batch mode, which I'll do at the end of the demonstration, which then results in a recommendation table being constructed specific to a user based on a predicted rating from the factorization machine model for a movie that they have not yet watched or rated. Factorization machines. A factorization machine, which I will reduce to FM or abbreviate to the initials FM for factorization machine, was first proposed in a paper published by Stefan Rendel back in 2010, who was working at Osaka University in Japan at the time. A link for that particular published paper called Factorization Machine should appear shortly for you to download your own copy. Hours of entertaining reading for the whole family in that one. So Rendel in 2010 specified that factorization machines can be used to generate recommendations and extend to other supervised modeling applications as well. Whilst it is almost most exclusively used for recommendation systems, that doesn't mean that it can't have other applications as well. Use your imagination. Imagine what other applications of this particular algorithmic technique could be used. One that springs to mind, and a very interesting one that I've read a few papers on, is applying factorization machines to sporting events, where you try and predict the outcome of two teams who have never played each other before, just as an example. Compared to support vector machines, which I'll abbreviate to SVMs, compared to support vector machines, factorization machines address the problem of large and sparse feature data in machine learning. Why is the data large and sparse? Well, it's large because for recommendation systems, we usually have lots and lots of different users or members, and we usually have lots and lots of items, or in this particular circumstance for the data that we're going to analyze, lots of movies. And it's sparse because most users haven't seen a great deal of movies, and most items or most movies haven't been seen by a large number of members. So in this very large user by item matrix, most of these cells in that user by item matrix are empty because a particular user has not seen a particular movie, therefore has not given it a particular rating. I'll talk more about the demonstration data that we will be analyzing later on in a bit more detail later. Factorization machines can accommodate two or more categorical input variables, such as users and items, which is the most typical application. FMs with two categorical variables are known as matrix factorization machines, and if they have three or more variables, they're usually referred to as tensor factorization machines. As I mentioned, factorization machines can accommodate more than just users and items. Try using other variables to improve your recommendations. This extends the classical model beyond just the user by item information matrix which everybody tends to use. So think about other features, other variables that you have in your data that you can include in your factorization machine, which may help improve the predictive performance. Matrix factorization enables estimation of all pairwise interactions, even though not all of the user by item ratings have been observed. As I mentioned previously, if we think about the user being a member or subscriber to a service, and the item being perhaps a movie that they might watch and rate, matrix factorization enables us to estimate a particular rating for a movie or an item, even if the user has not watched it. FMs estimate the parameters or weights using stochastic gradient descent. Now, I'm not going to talk about stochastic gradient descent as it's beyond the scope of this particular presentation. However, it's a very common optimization technique. Now, factorization machines actually have a closed form model solution, a closed form model equation, so that parameter estimates, so those biases and factor values, can actually be estimated or computed in linear time, unlike support vector machines, for example, which cannot. So it is relatively fast to estimate and converge. As an illustration, If we think about our user and item matrix, so we have the users are the rows in our matrix, the items are the columns in our matrix. The number of users can be extremely large, the number of items can also be extremely large. These matrices can be massive. I'll give you an example of Netflix in Australia a little bit later before we start looking at the demonstration. So if we think about a particular rating that a particular user has given a particular item, this massive sparse matrix can be factored or factorized into smaller, denser matrices. One user factor matrix, which is of size, number of rows is the number of users, and the number of columns is the number of user factors which we maintain or which we decide to keep, to retain, which is a hyperparameter of our model. And the second matrix which we can factor the larger matrix into is the item factor matrix, which has the size k, being that number of factors that we choose to retain, and the number of columns is the number of items. So a particular rating by user U on item I, not very good with letters, much better with numbers, is made up of a global bias plus the user bias plus the item bias plus any other interactions between variables which we may have. Algebraically, I did warn you that there were going to be a couple of equations in here. If we think of the user matrix as matrix V, the item matrix as matrix W, and the ratings for each particular combination of user and item as the matrix R, then what we have is a matrix V, which is a number of users as the rows and k factors as the number of columns. We multiply that by our W matrix, which is the number of rows is the number of items, and k, the number of columns, is the number of item factors retained, such that their product approximates R, where R is approximately equal to V times the transpose of W. That gives us our predicted ratings R hat. So the prediction of a rating of an item ij by user ui is simply calculated by the dot product of the two vectors corresponding to ui and ij. So our predicted rating rij for user I and item j is vi times the transpose of wj. So it's simply the sum of the dot products. Simply, yeah, sure. V and W, those two submatrices, which are factored from our ratings matrix R, need to be obtained. And this is what matrix factorization allows us to do. How does it do it? We initialize the two matrices with some values, the existing ratings, of course, and we calculate the difference of their product to R, the ratings matrix, and we minimize this difference iteratively. So mathematically, we have the equation, the residuals, Eij squared, so the difference between the actual rating and the predicted rating, Rij minus R hat Ij, squared, so it's the sum of the squared errors, it's the squared errors, equals Rij, so the actual rating minus the sum over all k of that dot product between V and W squared. So the difference is the error between the estimated rating and the observed rating, which we need to minimize iteratively using stochastic gradient descent. To avoid overfitting, typically L2 regularization is applied. So we add in the regularization penalty, which is the term on the right-hand side there, lambda on 2 times the sum over all k of W squared plus V squared all squared. that is an L2 regularization because we're using the square of the weights rather than the absolute value of the weights. What is regularization? Well, it's a technique that makes slight modifications to our learning algorithm so that our model generalizes better. L1 and L2 regularization, which is used here, are probably the two most common regularization techniques, although there are others. L2 regularization, also known as weight decay, because it forces the weights to decay towards zero. When talking about weights, I'm talking about the parameters in our model. So they decay towards zero, but they can't equal exactly zero. And lambda, in this case, is our regularization parameter. So the effect of regularization is to shrink the parameters, shrink the weights, and the weights are shrunk by an amount that is proportional to the size of the parameter. So larger weights are penalized more than smaller weights. L2 is not very robust due to the large penalties that may be applied to extreme outlying points. Okay, that's enough of that theory. Let's get our hands dirty and do a demo. In this demonstration, we're going to build a factorization machine using visual machine learning in order to recommend items, which in this case are movies, to users, which of course are subscribers to the movie service. Just think Netflix, everybody does. Consider Netflix in Australia. Now, I found these statistics off the internet, so they have to be correct. As at April this year, as at April 2020, in the Australian catalogue, apparently there were 5,164 unique movies. Now, I'm not sure whether that's just movies or whether that also includes episodes of series, but anyway, that's beside the point. There were approximately, because it's difficult to get an exact number of members, but there are approximately 11.9 million members in Australia as at April 2020. It's almost half the population, hard to imagine, but apparently that's what it is. It was on the internet, it's got to be right. So if every user rated every unique movie in Netflix in Australia, that's nearly 61.5 billion ratings. That's a big matrix. Now, the demonstration data that we're going to be actually analyzing in the demonstration coming up isn't quite that big. The demonstration data, which is a subset of the movie lens data, which can be found at http://grouplens.org/datasets/movie lens, consists of, now I'm actually using a subset of one of these datasets, 1,272 unique movies, 137,977 unique users, and our data set has 7,372,779 observations, which include a rating for each movie ID for each user from 0.5 to 5 with increments of 0.5. Now, if every user in this data set rated every movie, there would be the product of 137,977 by 1,272, which is about 175.5 million observations. Now, we only have 7,372,779 observations, so there's only about 4.2% of that user by movie matrix that actually has a rating. So our user by rating matrix is 95.8% sparse. So not only is it a big matrix, it's 138,000 rows by 1,272 columns, but only 4%, just over 4% of those combinations actually have a rating in them. Okay. So for the demonstration, I shall shortly switch to SASVIA, where we will use the visual analytics application to do some exploratory data analysis using a word cloud, and then fit a couple of factorization machines. One, firstly, just by using the default parameter settings, and the second one, I will tweak the hyperparameters to improve the performance. Then we'll extract or export the model and extract the scorecode and apply that to the data set outside of Visual Analytics in in SAS Studio. All right, as you can see, I've already logged into SAS Via and I'm at the SAS Drive screen, Share and Collaborate. I'm going to go to Explore and Visualize to go to the Visual Analytics application. I now need to specify my data source, which of course is the Movie Lens data source, which I was referring to earlier. It's actually a subset of one of the Movie Lens tables. If I select that, we can see that I have 5 columns in my data set and approximately 7.4 million rows. As specified earlier, there is exactly 7,372,779 observations. It is not a trivial data set to be analysing. The variables in the table, the unique user ID for each user, which is a numeric variable, the unique movie identification variable movie ID, which again is numeric, the rating, which is the value that has been given a movie by a particular user. This of course is also numeric and it has values from 0.5 to 5 in increments of 0.5. The title of the movie and the genre that the movie belongs to. Now, we won't actually be using genre in this particular analysis, so I'll be hiding that later. So I'll just OK that, which now loads my data into VA. Now, I won't be using genres, so I'm just going to hide that straight away so it doesn't get in the way. Title is a category variable. You can see we actually have 1,272 different titles, as was specified in the slide before the demonstration. Now, movie ID and user ID, because they are numeric variables, they are measures in Visual Analytics. However, they don't really have any numerical meaning. Therefore, I'll be changing their classification from measure to category. So now they are categorical variables, which makes more sense given that they identify either a unique movie or a unique user. We can see the unique counts there as specified in the earlier slide. And of course we have rating. We'll come back to the distribution of rating just a little bit later. But first, as every data scientist knows, before we even think about building any sort of a model, a very important preliminary step is exploratory data analysis. So I'm going to do a little bit of exploratory data analysis now. So I'll give my page the title of EDA for exploratory data analysis. Let's begin by creating a word cloud to get some sort of an idea about our movies. So in order to do that, I need to go to the Objects pane, and if I scroll down, I have Word Cloud. If I double click, that then creates my Word Cloud object. In the Roles panel on the right hand side, I'll specify the title, for my word, and I get my little word cloud here. Now the issue with this initial word cloud is that all that it's actually displaying in the cloud, the size of each movie title, is actually just the frequency of the title. So you can see that the values for the first 100 movies, the values range from 20,600 up to 68,700. This is merely the frequency or the number of times that a user has actually rated one of these movies. So these are just the most frequently rated movies, not necessarily the best or highest rated movies. The reason being is that because my default size is based on frequency, I need to replace frequency with rating, which will now display, that's very similar to the previous word cloud. Why is that? Well, again, because rating is a numeric, it is simply displaying the size is based on the sum of the ratings. And there is probably a very large positive correlation between the number of times a movie has been rated and the sum of its ratings. So that's not really informative either. In order to make our word cloud more appropriate for our exploratory data analysis, we should probably change the aggregation for rating from the default, which is simply to sum the values, to the average rating. So let's go back to our data pane. We find rating. We can see that the default aggregation is to simply sum the values. So that's not really helpful. We need to change that default aggregation to average. Now it will display the movies with the highest average rating. So we can see that the movies with the largest size will have the largest average rating. So ones that stand out on this screen, The Shawshank Redemption, The Godfather Part 2, The Usual Suspects. These are probably going to be the very highest average rated movies. We pick something smaller. Again, these will be highly rated because this is only displaying the top 100. So anything on this screen will have a high average rating, but the size will be proportional to the actual value from 4.046 to 4.449. Okay, now let's go back and take a quick look at the actual distribution of rating values. So let's go back to our data pane on the left and let's look at measure details. So we can see that for rating, which is our only measure variable, it has a minimum value of 0.5, so half a star out of 5 stars, I suppose you could refer to it as, and a maximum of 5, which would be 5 out of 5, with an average of 3.63 out of 5. That's for all movies, all 1,272 movies. The sum is not really appropriate or relevant for this analysis. And if we look at the distribution, we can see that there are peaks here at 5, 4, 3, 2, and 1 out of 5. So people tend to give integer ratings out of 5. However, it was possible to rate in 0.5 increments, in half increments. So movies can actually receive 0.5, 1.5, 2.5, 3.5, and 4.5. However, these are less likely compared to integers. And we can see that the vast majority of movies have values between, say, 2 and 5 in this particular sample. The mean, as we saw, 3.63. It has a variance of 1.09. There are 10 distinct values, which makes sense, 0.5 to 5 by a half. Slightly negatively skewed, so slightly skewed to the left, and virtually no kurtosis. Again, based on this sample of movies. Okay, let's close that for now. If we maximize our word cloud, we can see the details table underneath, which actually displays the highest ranking movies. So we can see that The Shawshank Redemption has an average rating across all users of 4.449, The Godfather 4.36, The Usual Suspects 4.33, Schindler's List 4.31, and The Godfather Part 2, 4.28 to 2 decimal places. So there are top 5 highest average rated movies. Why is this important? Well, one of the few disadvantages of factorization machines is what's known as the cold start. For a brand new user who has never rated a movie, we don't know what they like or what they don't like because they haven't given any rating to any movie yet. So this is considered to be a slight disadvantage as far as factorization machines are concerned, because obviously the more ratings a user supplies, the more we know their preferences to movies, types of movies that they may like and dislike based on their relative ratings. So what we can do in the absence of any ratings for a particular new user, we can simply offer as a recommendation movies that most people give a high rating for, such as these. This is known as a cold start. So whilst we don't know anything about an individual user's preferences, if we offer one of these 5 or top 10 movies, there's a good chance that they may like that as an initial recommendation. It's better than nothing. Let's restore that back down. And let's move on to building our factorization machine. So let's add a new page to our report. I'm going to rename this so I don't forget straight away. I'm going to call it FM for factorization machine. Now the factorization machine object is part of SAS Visual Data Mining Machine Learning. So there it is. So I'll add a factorization machine object to my canvas. And let's go to the options. So we can see that the initial options are just basically the way it's displayed, the layout. I will actually change the display from fit to stack, because I much prefer a stack where my output is tabbed rather than all tried to squash onto the initial fit screen. The statistics to show how well our factorization machine model fits our data will be average squared error. And if we look at the factorization machine options, we have, of course, auto-tune. Now I'll talk about auto-tune a bit later, but auto-tune basically allows the automatic optimization of the model hyperparameters. So when we're talking about factorization machines, the hyperparameters which need to be specified by the modeler include the factor count, so how many user factors and how many item factors are there to be retained. By default it is 5. The maximum number of iterations to converge to the optimal value via stochastic gradient descent, and of course the learn step, the lambda, the update weight. So these 3 hyperparameters can all be auto-tuned to find the optimal set of hyperparameters for a given data set. We're just going to run with the default model, so I'm not going to change any options apart from just changing the layout to stack. Let's go to roles. So as far as the factorization machine is concerned, all we need to add is our response variable, which of course will be rating, and our predictor variables, which will be the movie ID and the user ID. So once I OK that, it will start fitting our factorization machine just with the default settings. This will take a few moments. So my factorization machine model has now been fit. We can see from the summary at the top there, that the model that was used was a factorization machine. The average squared error from my model is 0.7494. Is that good? I'm not quite sure yet. There's nothing to compare that to. It's used all 7,372,779 observations. Therefore, there were no missing values. We can see by default, the iteration plot, which shows my loss function, which in this case it's an estimate of the average squared error. The final average squared error is displayed there in the summary tab. So it might be a good model, it might not. What is this graph showing me? Well, I can see that it has performed 30 iterations because that was the maximum value that I specified in my options pane. And since it is basically a horizontal line from the 15th iteration onwards, I'm fairly confident that it has actually converged to a solution. If it was still on a downward gradient, still decreasing loss function, then I would be tempted to increase the number of iterations. But clearly from this plot, it appears to have converged. So that's a good thing. The top recommendations. So the top recommendations based on this particular factorization machine, you can see that it's displaying 318, 858, 50, 527, 1221. These are the unique movie ID values. So in order to determine what movie that corresponds to, obviously we would need to find what titles those movie IDs correspond to. We can do that later. Our scored response shows us a heat map of the actual value for the ratings by the predicted values from our factorization machine. Darker values in our vertical bars represent higher frequency counts. So we would like to see, ideally we would have liked to have seen a diagonal line here with very little above and below, which would basically be a perfect model. But we can see that there appears to be a somewhat positive correlation between predicted value and actual rating. That's promising. Another way of displaying the scored response is via a histogram. I can right click and use a histogram to give us a look at the distribution of our predicted ratings. And there we go. So we can see that appears to have a slightly negative skewness, as did the original ratings. We have values down to about 1 out of 5. We have values also at the upper end which exceed 5. Now, of course, this is not going to be a perfect model. The factorization machine itself does not know that it can't produce a prediction greater than 5. There's no constraint there. But if we're using this as a recommendation engine, there is no real issue if we have predicted values for movies greater than the upper cutoff. It just means that obviously the factorization machine is predicting that this user will really like this movie. So whilst not ideal in that we are getting predictions outside the range of our target or response variable, it's still not that big a deal. So there's our nice distribution of predicted values. And if we look at our assessment, so assessment takes our predictions, ranks them from highest predicted rating to lowest predicted rating, bins them into 5 percentile or demi-decile bins, and then plots the average rating within each of those bins versus the actual or observed average rating within that bin. So again, if we had a perfect model or an ideal model, those two lines for the blue line and the gold line for the predicted average and observed average would actually be on top of each other, they'd be superimposed. So, you know, yes, it's a model. All we did was run the defaults, remember? So we can't be too harsh on performance. But we can see that we're over predicting at the top end on average. We're right here, that's fantastic, but now we're under predicting on the lower end. So, but hey, we just use the defaults. What can we expect? Can we do better than just the defaults? Well, I'm sure that we can. Let's go back to our options. Now, with factorization machines, I mentioned earlier that only about 4.2% of our data values actually exist when we look at combinations of every user and every movie. So nearly 96% of our user by movie or item matrix is empty. One of the things that we can do to improve our predictions to fit a better model with highly sparse matrix is by using non-negative factorization. It's going to use non-negative factorization. I'm also going to increase the number of iterations to 100, but I am going to increase the learn step to 0.01. Now this will refit our model. Remember that the default model gave us an average squared error of 0.7494. So let's go back to our iteration plot. And this will take a few minutes to fit, especially because I'm doing more iterations. However, I have also increased the learn step by a factor of 10. Let's just wait and see what the results are like. Okay, so my model's finished, and as you can see, there has been quite a dramatic decrease or improvement in fit of my factorization machine model. The average squared error is now down to 0.6164. So that's a rather dramatic improvement from the default option values there. You can see that my loss function decreases very quickly initially, then still improves but at a less steep gradient, and it appears to have flattened out. Yes, it does appear that it might still be on a slightly downward trend there. I could, I guess, increase the number of iterations a little bit further, but for the purposes of this demonstration, it certainly flattened out, and that is a definite decrease, I should say, not increase. It's a definite decrease in the average squared error. It's a definite increase in improvement in model fit. Let's look at the recommendations. Recommendations, I don't know how good your memory is, but they're basically the same set of movies. 356 might be a new one perhaps, but those numbers certainly look very familiar. So it hasn't really changed the prediction of the highest average rated movies. That's a good thing. You might be asking yourself, what was that non-negative factorization option that I selected? Well, non-negative factorization forces non-negative factors. So the user factors and the movie or item factors must be greater than 0. And all the bias terms, so the global bias, the user bias, and the item bias are set to 0. Okay? You will find if you have extremely sparse data that on some occasions, obviously it's not a one rule for everything, but on some occasions it's definitely worth trying non-negative factorization to see if that improves the model fit. In this case, as you can see, it definitely has. The scored response. The shape of the distribution looks similar to the previous model. However, I think we might look as if we've got fewer. Yes, indeed we do. So we have fewer predictions greater than 5. That's definitely a good thing by the looks of it compared to the previous model. And on the lower end, hard to say whether there's much difference there. Still seems to go down towards 1 star or 1 out of 5. but definitely a better fit to our data. All right. If we maximize, we can see our values for our hyperparameters. Now let me just talk quickly about the auto tune option. When you're not really sure what to use for the model settings, then auto tuning can find optimal values for our model hyperparameters. Hyperparameters are the settings for the model fit. So for a factorization machine, that will include the number of factors to retain, the maximum number of iterations for convergence, and the learning step size. Auto-tuning, which is available across many types of models, uses a genetic algorithm by default. You can also use a Bayesian technique, but by default it uses a genetic algorithm based on a Latin hypercube to optimize settings for a wide range of model hyperparameters. Using auto-tuning can dramatically improve models, although if you use it on extremely large data, then obviously because it is fitting a multitude of different combinations of hyperparameters, then learning can be slow, or slower I should say, because it is fitting multiple models. So one approach could be to perhaps use only a smaller sample of the data, auto-tune on the sample, and then apply those values to the larger data source. Of course, that would not guarantee that that set of hyperparameters will still be optimal though. But it could be a useful guide as a starting point. Finally, if we move along to the last tab in our output, the assessment, we can see that with this new model settings, the alignment of our predicted average rating in each of our 20 bins compared to our observed average rating in each of our 20 bins is much, much closer. So if you remember from our previous default model, for about the first 40% of our highest ranked average ratings, our model was over predicting, and then for the bottom about 60%, bit less than 60%, it tended to be under predicting compared to the observed average rating in each bin. But now we can see a much, much closer assignment. Much, much better. And that of course is reflected in the rather dramatic decrease in the average squared error of the model overall. Much better fit. Okay. If we go back to our top recommendations, it might be interesting to see which movie titles correspond to the top 5 or so movie IDs as far as the predicted ranking is concerned. So in order to do that, let's add another page to our report. Let's go to our objects pane, and we want to add a list table to our canvas. In the roles pane, under columns, we want to add movie ID and title. There's all of our movie IDs and all of our titles. Obviously, we're only interested in those top 5 or so from the predicted ratings. So in order to just display those, we're going to add a filter. So we go to the filter pane on the right hand side. We need to add a new filter. That filter is going to be based on movie ID. Now we don't want to include missing values, and we don't want to select all. So let's deselect select all. Let's go to an advanced edit, because we're only going to specify certain movie IDs. We click in none selected. Okay, only the 500 most frequent values are listed. That is fine. For our first movie, that was movie number 318. So up here, let's type in the movie ID 318. Click the search icon. There it is. Let's add that to our selected item. Second one, 858. In fact, we can just add the plus sign and that will add it in as well. There it is. 50 was another one. 527. 1221. And that new one that I don't think appeared in the top, in the default model, 356. Okay, so we're only going to display now those rows where movie ID is one of those 6 values. So I'll just OK that, and OK again for the filter. And there they are. So those top average predicted rating for those movies, The Usual Suspects, Shawshank Redemption, Forrest Gump, Schindler's List, and The Godfather and The Godfather Part 2. They should sound very familiar because they were the movies that were identified as being very highly rated just from the word cloud, just from our exploratory data analysis. Good to know. Consistency is a good thing. Let's move on. Now, as I mentioned earlier, if we know nothing about a particular user, if they're just brand new and they haven't rated any movies yet, then using the highest average predictions for a movie, known as a cold start, is probably the best that we can do as far as recommendations go, because we have no knowledge as to what they like or what they dislike. Okay. Let's save our model and our user predictions. So we can save the predicted ratings for each user to the data in memory for the movies in the data. Let's go back to our factorization machine. If we click on the snowman in the top right, we can derive predicted. So this way our residual and predicted values for our ratings will be saved to our data set. That's done. Let's open a new page. And we're going to add a list table. On the rows on the right hand side, the columns that we're going to add to our list table are the title, the user ID, the predicted rating, and the rating. So now for each of our movies, and the first ordered movie is Till There Was You. Can't say I saw that one, but he's been rated by certainly more than one user. We have their actual rating on the right hand side here underneath rating, as well as the predicted rating from the model. So if you just want to take a quick eyeball of the difference between the prediction and the actual ratings, not too bad at all. Now we're going to filter this. So let's create a filter. It's a new filter. It's going to be based on the predicted rating. And we just want to clear the checkbox for include missing values, just in case there are any. Couldn't be scored. That will filter out those cases if there were any. Let's return to the factorization machine page. And what we want to do now is to export our model. So now if we click on our snowman, not that bottom snowman, that's the wrong one of course, we want to export our model. I'm going to call this model Fact Machine once it's ready. Okay, let's give this the title of Fact Machine as opposed to the default. Okay, let's give this the title of Fact Machine rather than the default. And okay that. This pops up the export model window. The code in the export model window is just a SAS program that can be used to score the data without actually refitting the model. There we go. We have a series of macro variables here to specify settings. We have a cas connection here, runs proccazutil to load the A-store table, and then it runs proccas to actually fit the model. So I'll just export that. And it's done. Now to actually apply that code, let's go to develop SAS code, which is SAS Studio. There we are. Now, if I go to, I've saved this one earlier. If I could go to SAS content, users, that's me, my folder, my snippets. Here's one that I've saved earlier. If I double click that, Factorization machine score code, you'll see that this is now going to score my movie lens dataset. So if I submit this, it's still running. So there is our output CAS table with the 6 columns, including the predicted rating from our exported model code, and of course the 7,372,779 rows from the original data set. If you want to take a quick look at what that data set actually looks like, then if we just go to our libraries, CAS user, there it is, and we can see that here's our 6 columns: user ID, the movie ID, the rating that the user gave that particular movie, and the predicted rating from our model. Okay, so in summary, factorization machines estimate a large number of parameters by using matrix factorization on very sparse data. The data that we analyzed was the movie lens data, which consisted of a very large number of users, a large number of movies, and in that user by movie matrix, only about 4% of those cells actually had a rating. Therefore, the sparsity of that matrix was around about 96%. The data are sparse because most users haven't seen more than a few movies, comparatively, and most movies haven't been seen by a large number of users. Factorization machines can accommodate more than just users and items. You can actually include other predictive variables as well, which will improve the performance of your factorization machine. Things like demographic data, for example, or Predictions from other models. These can also be included in your factorization machine model, which of course again will improve prediction and performance. This extends the model beyond just the usual user by item information matrix and can lead to better predictions, better recommendations. Matrix factorization enables estimation of all pairwise interactions, even though not all of the user by item ratings have actually been observed. This makes it somewhat special. Parameters or weights are estimated using stochastic gradient descent. And since there is a closed form solution, then results can be found in linear time. Increases in complexity of our model also simply result in a linear increase in time, as opposed to other modeling techniques such as support vector machines. We looked at a demonstration of how easy it is to actually fit a factorization machine using SAS Via. Even with the default hyperparameter settings, we created an adequate model. However, of course, knowing how to tweak those hyperparameters, or alternatively using auto-tuning, can vastly improve the predictive performance of your factorization machine. In fact, any predictive model. The model can be exported very simply by exporting the model, which generates score code, which then can be run in batch mode, for example, as a SAS program to score external data. Any questions? Please feel free to ask any questions now if you haven't already. And on the slide there, you can see there is multiple methods of contacting Selerity if you're after more information regarding anything that's been discussed during this webinar.